For public key cryptography, we just need an operation which is one way, so that you can do it very easily this way, but very difficult to do that way. And one of the things which people figured out is that you can add 2 points on a curve much easier than find the 2 points if you were given the sum or something like that. Or, or find a difference, whatever. So the way it is defined, the sum is defined is that you take any 2 points and the sum is defined that you first draw a line, see where it intersects, and then find a mirror. So P plus Q is this point. It's strange, but that is how it is defined. If you want to add P to P, so what you do is you bring Q as close to P as you can. When you bring next to it, then it will become a tangent line. That tangent line will intersect someplace, and the reflection of that will be 2P. You add 2P to P, that will intersect someplace, find the mirror, that will be 3P. So you can do the addition. It's not straightforward, it's a lot of math there to do that, but it is doable. But given 3P, it is very difficult to find P. But here's the thing, so if I gave you P, you should be able to find 2P, 3P, 4P, 5P by simply finding the tangent, finding where it is intersecting, doing the reflection. You have to do all that, but it is doable. If I give you 3P, find P, you'll be doing it forever. You won't be able to find it with any computing power, right? You will be able to find it, but with the current computing power, it will take quite a bit of work. So that's the whole theory behind elliptic curve over real numbers. It's very easy to add, but very difficult to do the opposite of the add. RSA method was based upon similar principle. It is very easy to exponentiate, but it is very difficult to take log, which is the inverse of exponentiate. So here it is the add and the inverse of the add. So now here's the curve. Y square is equal to x cubed plus ax plus b. You can just select whatever a and b value you want, and you got your own elliptic curve. A and b are not secret. Everybody knows a and b. So probably that is not the secret. What it is that you should select a and b such that they don't make a curve which is not useful at all. If you select this, then the curve will not be useful. And I haven't figured out actually what curve it will result in, but basically that is not a good set. But if you select any other a and b, then you follow this principle, then you can do all of these. This is basically a Galois field, which means finite field, and that means it's all those 8 conditions of, I forget, 5 plus 7, 12 or 13 conditions, starting from the additive identity. All right, additive identity, by the way, is infinity right there. That's the additive identity. When you add P to this point here, you get a P. Because this and that point, the intersection is at, that point, somehow, here, and then deflection is right there, back. So that acts as an infinity. And so some books, actually, for example, Wikipedia writes it as infinity, and the book writes it as 0. So you have to choose your thing, whether adding 0 makes sense or adding infinity makes sense. But the point is at infinity, but when you add, it doesn't change the point. Okay, so it acts like a 0. So to double a point, you find the tangent and the intersection. For a closure, you take P and Q. If P and Q are on the curve, then the sum will be on the curve. And P plus 0 is P, and minus P exists. So for every point, you can find out the negative of it. So that negative is such that if you add to it, you will get infinity. And then commutative means P plus Q is Q plus P. So whether you add P to Q or Q to P, you get the same thing. If you really want to do P plus Q, you do have to do a lot of math. And this is the math, is that you have to calculate delta, which is the slope of this line, yq minus yp divided by xq minus xp. Then you can solve the equation of intersection where this line intersects the curve, and it will come out xr is equal to delta square minus xp minus xq, yr is equal to where r is this point right there. If you want to do 2p, you can put yp is equal to x, yq is equal to yp, right? And then you will find out that the solution is xr is equal to so much, yr is equal to so much. So you really have to put these numbers, you have to program these formulas. I don't think you can put it in your brain, so you'll have to put this in your piece of paper that you bring to the exam. Because if I ask you what is 2p, you have to calculate it. And these are the formulas. So everybody now feels comfortable that given p and q, they can find p plus q. And given p, you can find 2p. Now if I gave you this thing, 2p, then you cannot find p. That will take some time, right? So that's the key thing. But we're not going to do it in the real numbers. See, the graph that I showed you here, that was over the real number, so p and q could be any point. What we are going to do is over finite fields. So just like we did the mod arithmetic, instead of mod arithmetic, here we are going to do it in the finite field, Galois field. And so here the points are defined over ZP. What is ZP? ZP is those numbers mod P, basically. ZP is mod P, nothing else mod P. So ZP includes 0, 1, 2, 3 up to P minus 1. P is a prime number. Or it could be Galois field 2 raised to n. And we have done that in AES, Galois field 2 raised to n, and then you have to put some polynomial. Whenever you do Galois field 2 raised to n, you have to say what polynomial we use. So you define EPAB over ZP, and you use the integer arithmetic modulo the prime, and you can easily implement that in software. So that actually is in some sense might be easier than some of these formulas which really require a calculator of some kind, right? So, and similarly you do on the binary curve, if you want to do a prime curve, so this one uses a prime number field, or you can use a binary field, 2 raised to n. In this case, you will use a polynomial, and then you can easily implement in hardware. Polynomials are not very easy to do in software. So they have two choices for you. If you are doing it in hardware, you use Galois field 2 raised to n. If you are doing it in software, you use Galois field over prime number. Now, addition in elliptic curve is similar. Now, similar is not the same. Is similar to multiplication in integers. So we saw that, right? You can very easily add, you can very easily multiply. And you can add many, many times, and you get, k times p, right? And you can multiply many times, and you get some number raised to d, or e. So exponentiation is very similar to repeated addition, right? And the opposite is difficult. So you cannot do inverse exponentiation. Similarly, you cannot do inverse addition. So that is similar to this discrete log. So let me give you an example of how this will be done. And this we will take the example of x cubed plus x plus 1 mod 23. Again, you can take any curve which is of the formula y square is equal to x cubed plus ax plus b. This is very similar to what we had in the real arithmetic. And a and b have to follow exactly the same condition that we had before, that 4aq minus whatever number. But so we can select a equal to 1 and b equal to 1, and we get this curve. So we call this elliptic field over 23 with a equal to 1 and b equal to 1. So the notation is that you put the modulus as a subscript, and you put a and b as the parameters. So this is our field. Now, if you just calculate the positive numbers that satisfy this thing, y square is equal to x cubed plus x plus 1, you can put x equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to 22. You will find the y values, right? And these are the points you will find. These are the total number of points. This is it. There are no more points on this curve. Actually, the curve there is not a curve wave because they are not connected. They are just points. Now, one interesting thing to notice is that when you put one value of x, you get two values of y. Everybody sees that, why you get two values of y? For every value of x, you get two values of y. Y square. Because you get y square and then you get a plus and minus. Obviously, we don't take minus. To remove minus sign, what we do? We add the modulus. Right? So when you put x equal to 0, you get a 1, and you also get 22, minus 1. When you put x equal to 1, you get a 7, and you get a 16, minus 7. Okay? So you can write down 0, 1, 2, 3, 4, 5, 6, 7, 8 doesn't create a new point, so it doesn't exist. And 9, 10 doesn't create. So let's just put 8 and see what happens. If you put an 8 raised to 3, 8 cube, 8 raised to 3 is 2 raised to 9 is 512. 512 plus 8 is 520 and 1 is 521. The square root of 521, let's see. One can try it, but probably doesn't exist, okay? And therefore that point doesn't exist. So we have 8 missing, 10 missing, 11, 12, 13, 14, 15, 16 missing, 17, 18, 19, and then 20, 21, 22 are missing. So this Galois field has only these many points. Now you can take any point and you can add those points. However, the addition is not that modular addition. If I ask you to add 0, 1 and 0, 22, you have to go back to this formula business. You have to find where this will intersect and there is a reflection. So if I ask you what is the sum of these 2 points on the Galois field upon an elliptic curve, you have to find the sum over the curve. That's the complication. So you have to use again these formulas. Just like now here, the book keeps changing the notation every section of the. So they change it from previously it was delta, now it is lambda. I registered my urge to keep the notation same, but if I put delta here, students are going to get confused and they cover the book. But if I would write the book, I would put delta everywhere, same thing. Like in the previous slide it was delta, now it is lambda. So anyway, lambda is this, and then you calculate using this formula. So if you want to add 310 to 97, you put those 3 and 9 and 10 and 7 in the formulas and you get 712. If you put P equal to Q, then this will be 0 upon 0. P then equal to Q, then you use this formula, the top formula, and if P equal to Q, then you use bottom formula. Whenever something is 0 upon 0, we have to find that. Okay, so maybe there's a typo here. Maybe I didn't use 310 and 97. Let's see what did I use. I used 310 and XR is equal to lambda square minus 3 minus 3. So actually I probably did 2 times 310. Did I use 9 anywhere here? So there's no 9 in this example. Alright, so basically, thank you for finding that out. What I am doing is actually 310 plus 310, I think. Let's just, basically in your notes you can correct that. I'm not calculating 310 plus 97, I'm calculating 310 plus 310. It should be YR equal to lambda times XP minus XR, which would be 0. Sorry. Yeah, this is correct. So this is XP minus XR. Remember, this R is the one that you calculated just a minute ago. Okay, so this 7 is this 7. That if I use this formula for P equal to Q, then it will come out 0 upon 0. That's why this formula is not used for P equal to Q. So that's why this top formula is for P equal to, not equal to P, not equal to Q. And this is, doesn't even have a Q here, so this is for P equal to Q. Alright, so now you know elliptic curve. Now this is all very deep cryptography, by the way, and this is also very new cryptography. Because the previous book that we used in the last offering of this course, elliptic cryptography was future. And now it is here because there are standards which use elliptic cryptography. So it's important that we use this book and that we get this latest thing. Now once you understand elliptic cryptography, then you can do everything that we did in the multiplication domain, in the previous RSA business, with elliptic curves. So for example, Diffie-Hellman. If you remember, Diffie-Hellman was where what we did was we selected the random number and then we sent some power to the other side. Other people, they're listening everything, but they could not take the anti-log. Right? And the other side to select another random number and send us back some power, and then we could both agree on a random number. Same thing you can do here, but with additions now, elliptic additions. So what you do is the A selects a random number A, NA, and it selects a a G, which is the X1, Y1 generator, and generator has to be such that the order is n, is large. Okay, so it is not a primitive root. I mean, it could be primitive root, that will be good, because with primitive root you are guaranteed that it has the highest order. But if it is not a primitive root, in the example that we had some numbers, like in the example, we are going to the powers of all the numbers up to 5, right? Some numbers have the square equal to 1. That's not a good number, because they will remain 1 forever. On the other hand, if you take the primitive root, then it will cover the whole field. But here they are saying you don't need to take a primitive root, you just take a number such that the power is large and the order is large. And when you say order is large, means ng equal to infinity. Remember this, you have to just don't get confused. N times g means when you add g plus g plus g plus g plus g plus g plus g, you will get the identity, and identity is O. O is that infinite point. So basically, so you find the number, and generally, I mean, there might be a whole table built in beforehand, and people will just select one number from there and then do. A and B select the private keys, and A and B. And A and B are the numbers that they have selected themselves. And so you send in the public G, Q, A, B, and Y, A. So G is your generator that you selected. Q, A, B basically makes sure that, now here again, the author, the book author, changed the symbols. A minute ago we were using P and Q for the points. Now he's using Q for the base. Where we were using little p. I mean, I have written books, and I just want to make sure that we use one consistent notation throughout the book, not alone that we switch in the same chapter several times. So the Q here is the base, 23, like we were using before. A and B are those parameters that we selected for the elliptic curve. So this is basically specifying the elliptic curve. And then YA is the calculation that we did. What we did was we calculated YA is equal to NA times G. So this is like exponentiation in the RSA world. Instead of exponentiation, we do addition n times, NA times. We send this out. The other side selects another number NB, and it does similar addition NB times G. The G is given. And then it sends that by V back, and itself calculates MB times YA, and that is the secret. Other side does the same thing, NA times YB, and that is the secret. Both the secrets are same, except the rest of the world cannot calculate that because they don't know NA and B, and they cannot do the inverse. So whatever we were doing the exponentiation, we are doing it here with the addition. Okay, Q is this letter here. Q is the modulus. For elliptic curves, you need 3 parameters. AB, which are used in this equation, y square is equal to x cube plus ax plus b, AB, and you need the modulus, right? And if you have the modulus, whatever modulus is, you put that as subscript. So you say E subscript P AB. So here it was being used as P, and then next slide they're using it as Q. And some other things in fact, we do this in our writing of our paper, and I would recommend that you do it in your own writing of your paper. Keep the cases consistent. If uppercase means a point, then a number, then uppercase means a point and number. But here they just keep mixing up cases as well. Capital G, a generator, and some other place, some other number. So I haven't basically. So the thing is, book is just, I think it was written in pieces by different people. And by the way, Starling writes 20 books a year. So you know who is writing the books. So, so there's a whole factory. So what happens is when the factory is assembled, this is what happens. But books are good. Having said that, is that in the sense that he has a standard that he checks out, that there are good examples, good exercises, good supply of the material for the students, good supply of the material for the professors. It's very difficult to do for one-person factory like mine. There's nobody to help. You get this, right? Where are we? So everyone knows how to do Diffie-Hellman in the elliptic curve. basically you select the initial number like we used to do before, and you select a power or something like that, and then you select the raised to that power and send it over. Here you're just going to do the addition and then send it over. The other side will do some more addition and then send it back. And I keep saying addition times multiplication. Actually, MB times G is multiplication, but I don't want you to confuse with that. It's actually G added MB times. G plus G plus G plus G plus G. And it's not just a multiplication in the normal sense. So I won't use the word multiplication when we're talking about elliptic curves. All right. How do you do encryption and decryption? Exactly the same way, just like we did before, except that just instead of the quote multiplication, we use addition. So here is it. So there are several alternatives, and one is that you select a curve in a point G and encode any message M as a point on the elliptic curve PM. So you find out the and I hate this again, PM. This should be capital EM. But anyway, so each user selects a private key NA, and then public key CA, which is NA times G, and therefore then encrypts as CM plus KPB. The K is a random number, and sends out this thing, K times G plus PM times KB. To decrypt, you can compute, you can decrypt the cipher text PM. Now here's the confusion. Let me see. I think maybe I'm confused, or maybe Arthur is confused. Key is the plain text, and so the curve should be EM, the point should be PM. Select M as a point PM on the elliptic curve EM. Anyway, so the P is a point PM, and that is calculated like this, and then the decryption is done the opposite of it, because if you know KG, let's see, what you do is you take the second part minus your private key NB, minus the public key is PA and the private key is NA. You take the private key of B and multiply by the first number, and so anybody can do this. So then you can do the decryption back. So if you know the second key NB, the decryption is trivial. If you don't know NB, then obviously you cannot do any of this. So let's just double check the mathematics. PM plus K times PB minus NB times KG, and KG, so B knows G, B can calculate NBG. Nobody else can actually, so that's the thing. So, and B knows NB, and B can calculate obviously KG here. So B can calculate all of this. User selects NA, which is a private key, NB is the other private key, and user computes for any random K, computes this quantity and sends it over. So you just to think about it a little bit more, but basically that's what it is being they are doing here is, let's just think in terms of RSA. So what we are doing in RSA world. What we are doing here is that this is an exponentiation. So we exponentiated G to the power K, and this is similar thing. The main thing is that since we did two things here. Actually, this is what is happening, and this is, if you think it this way, there are two steps. First, you have to agree on a secret, and then we use that secret key to raise to some power. In this example here, we are doing both at the same time. So we are, instead of having any secret, we are selecting a random K number K, and then sending KG here. We selected NA, and we selected NA times G. Send it over, right? And using that somehow, it finds out YAB and so on and so forth. Same thing here. What we are doing is we are sending G and K. K, we are not sending K. We are sending G and KG. G is already understood. So once we know that, then basically that sets up, the privacy, and if you work out that same Diffie-Hellman followed by the addition, you will find that this is true. Okay? So this brings up the encryption and decryption. And you really need to do one exercise before this all becomes clear. The right way to do it would be to break this into two pieces where you just send KG first. If you send KG first, then I can determine the key. Then you send the second part. At that point, we can just use that part to decrypt. But instead of that, we are doing both of them in one step. So the secret is being sent as well as the encrypted text is being sent. And again, the notation is confusing. Please bear with me. I don't know what to do. I just want to follow that is in the book so that when you later on you go. For example, I would not use PM as the plain text and PB as the private key, public key of B, and PA as the public key of A. Same letter P is being used for many things, for the key as well as the text. PA and PB are the keys, PM is the plain text, CM is the cipher text. Okay, yeah, right. So everything is, after all this mathematics, you should get one of these points. So this mathematics looks complicated, but when you do this, you get to one of these number of points. Now, obviously, you won't have this table because there's no number 23. It is 23-digit number, maybe a 230-digit number, right? So these are all very difficult addition and multiplication in the real world, right? Having said that these are really large numbers, it turns out these are smaller than RSA numbers. Because if you do 56-bit DSA, you can get similar kind of encryption strength by 112-bit ECC. You will need 512-bit in RSA. So RSA requires a lot more because it's much easier to multiply than to solve those equations that we just saw a minute ago. Right? So with 112 bits, you get same kind of strength. So you can keep seeing that, here you will need 15,000 bits where you can do it in 512 bits, and with secret you can do 256. So ECC reduces the key sizes. All right, now this is a topic which actually should not be in this chapter, but since the book has this in this chapter, I am covering this, how to generate random number using asymmetric ciphers. So we know how to do it basically, and you just have to feed something to any of these ciphers, whatever comes out is random. And whether it is symmetric cipher or asymmetric cipher, it's the same thing. So basically, you can use asymmetric ciphers to produce random numbers. It is much slower than symmetric, as you saw, because there's so much calculation involved, and therefore you generally don't use it to generate one-time pad or anything like that. You use it to generate the key for the symmetric. So, for example, if you wanted to generate using RSA, that's a standard, X9.82, and the way it does is you feed any seed X0, and every time you seed is different, the whole sequence will be different. But you feed a seed and you select some parameters for the RSA. If you remember, RSA has the parameter n. N is for what? Is the modulus, right? E, now if you know n, what is E? Which key was this, public or private? E is for the encryption, so that is the public key. D is for decryption, so that was the private key. R and K, N, E, R, and K. E and N, this is the public key, R and K. X raised to E mod N, R and K. So R and K are actually parameters. There is nothing with RSA. Basically what you do is, you select R and K and you take the K bits and feed back the R bits. So R plus K must be equal to the size here of the number of bits that you are going to get, R plus K bits. output. So you take the key bits and you use them, and you take the R bits, take it to the next seed, do the same thing, take the K bits, R bits, take the next seed, and you get a certain size random number. Now you can do the same thing on ECC. Now for ECC you have to do similar things, except that instead of multiplication and exponentiation, to do addition and repeated addition. So there is a standard, by the way, X 9.82. This was also X 9.82. So that standard specifies both RSA and ECC, 18031 as well as all of these. Anyway, so all of these specify this ECC-based stuff, and so the notation is X of P means X coordinate of P. LSB, least significant I bits of X, is equal to I least significant bits of X. So that's the notation in this graph here, in this algorithm here. Algorithm is for I equal to 1 through K, do Si minus 1 times P, X coordinate of that. So you take a point P, add it Si minus 1 times, and take the X coordinate, that becomes a new Si. And then you take Ri, which are the least significant 240 bits of X, SIQ, Q is the other point, and you take least significant, and so then you return these. So this is basically similar to this. Here we were taking K bits, and there we are taking 240 bits. So K is equal to 240, and the rest of them are being fed back. So basically this curve, basically this keeps circulating around, and then you keep adding the bits, and that becomes random numbers. So you keep repeatedly adding, multiplying P by Si minus 1, which means adding P Si minus 1 times, and adding Q Si times, and you return some Q. So anyway, that brings to the end this chapter. 5 key points. First point is the Diffie-Hellman key exchange allows creating a secret in public based upon exponentiation. And so actually now we can generalize it. It is not just based upon exponentiation. You can use it by any other method, but the original one was based upon exponentiation. In 1976, when we did elliptic curve cryptography, this was based upon exponentiation. ElGamal uses that for cryptography, and then elliptic curve is based upon defining addition of points on the elliptic curve. It could be either GF3 or GF2N. Anybody remembers when we use GF2N? Yeah, hardware. You can be loud and confident. Hardware. GF2N is done in the hardware, GF3 is done in software. And public key, why is it done in the hardware? Why? What is the thing? Because in GF2N we need mod a polynomial, right? You just don't do modulation with respect to 2 raised to 8 or whatever. In AES you saw that, how we do mod 2 raised to 8. I think it was 2 raised to 8. There we had a polynomial. All right. So public key cryptography, both RSA and ECC, can also be used to generate pseudorandom numbers. Any questions about this part? So this part was called other methods of public key cryptography. So other method means other than RSA. RSA is the most common method today, but these things have come up. For example, ECC was not there a few years ago. It was a concept. It was more in theory. It was more in paper. But now it is in standards. It is being implemented.